Swayam Prabha. Digital India. Educated India.
Alright, so I'm going to go over quickly again this example of feedback passivation that we did. This is on the standard Euler-Lagrange model for a robotic manipulator. Okay, so this is a very general model. If you remember, we talked about this. You can use any kind of coordinates. That's why they're called, the Q's are called generalized coordinates. They could be the angle coordinates or they could be the linear coordinates. Yeah, so your robot could have this motion, or it could have, you know, sort of elongation, and you know, you can have a pneumatic actuator which sort of elongates and, you know, gets bigger and so on and so forth. Or you could have then, or you could have spherical joints, whatever. You can have different kinds of variables, and that's why it's called generalized coordinates. It's not just Cartesian coordinates, it's also maybe angle coordinates, and it is very much possible to write all of them in this form. Yeah, no problem. Yeah. The only cases where you cannot write them in this form, the robot dynamics in this form, is typically the non-holonomic cases, yeah, where you have some non-holonomic constraints. We have not talked about those, so do not worry about it. In those cases, the model looks different, yeah, because there is some, you have to have redundant variables because there are non-holonomic constraints. So that is the only case where you will have different kind of models than this one. But otherwise, most robotic manipulators can be modeled in this. In fact, even mobile robots can be modeled in this if the wheels are of if it's an omnidirectional robot. Yeah, if you have an omnidirectional mobile robot, that can also be modeled like this, no problem. Okay, so that's sort of the nice thing. This encapsulates a lot of different systems. Okay, the control is on the right hand side. Typically, you will see the control as being motors mounted on the joints for angular motion. For linear motion also you can have linear actuators. Okay, so that is the control, typically like a torque or a force. Okay, all right. If you remember, I mentioned that this M matrix is the inertia matrix. It is symmetric and positive definite always. Okay. C is the damping, well, C is not the damping, C is the centrifugal and Coriolis forces, okay, and D is the viscous damping. Yeah, we are not a modeling course, otherwise we would have talked about how to arrive at these matrices. So we are not going to talk about how to arrive at these, we will just give you some of these matrices. Alright. G is of course the gravity term. Yeah, if gravity is a factor, then you have to add the gravity terms also. Alright. One of the facts that is known about this model is that m dot minus 2c is skew symmetric. Okay, what's the value of this? It means that any quadratic form that you construct with any vector eta on a skew symmetric matrix, that is 0. Okay, quadratic form of a skew symmetric matrix is always 0. Okay, this is again standard result. All right. Suppose the aim is to track a constant reference. Yeah, I was careful, we discussed this. If it's a time varying reference, then you have to do a little bit more jugglery, it's not this simple. So if you have a constant reference QR, okay, then your error model, yeah, error is Q minus QR, the error model actually looks exactly similar. Okay, again because I chose a constant reference R, that's it. If you chose time varying, you will have to slightly modify how you work with this problem. Yeah, we may look at it later, but not right now. Yeah? So constant reference model would mean that it's a what we call set point regulation problem. Yeah, it means I start at some configuration and I end at some configuration. Okay, I give a start configuration and an end. So whatever you folks, if you work with quadrotors, typically you give waypoints, right? It's this. You go from one waypoint to the other. You are not giving a trajectory in between. Sometimes, but more often than not, you would also want to specify the trajectory in between, so that you are not following very bad trajectories to reach from one point to the other. That is not covered here. We are only going from one set point to another set point. Okay. So that's what this QR is. You construct an error, you get the error dynamics. Yeah. And we want E equal to 0 to be globally asymptotically stable here. Alright. Okay. For some Kp equal to Kp transpose positive, we consider this control law for feedback passivation. Okay. What were we doing in feedback passivation? We were saying that we will specify the control so that the resulting system becomes feedback passive in the new control. Okay. That's what we are sort of doing. Yeah. I am already saying what U is. Yeah. Because I know this will work. So this is GQ minus KPE plus V, which is the new control, and I am going to claim that the system is feedback passive with this control and some output. We have not yet decided the output either. Alright, output is not decided either. If I plug in this control, what happens? If I plug this in here, what happens? This and this cancel out, right? And this KPE goes to the left hand side, becomes a positive term. Okay, that's it. That's what I have written here. Okay. So now once I have this structure, and I know this is a very nice structure, even for you it should be evident it's a very nice structure. Why? First of all, M is positive definite. Yeah. Always the term on the highest derivative should be positive definite, symmetric. Yeah. It's already nice. Think about the Routh criteria. It's all generalization of that only, because it's almost a linear looking system. Not very non-linear actually, it's almost a linear looking system, right? Because this is E dot and again a E dot, and then you have an E double dot. And the second order almost linear looking system. Yeah. And also the term in the connecting to the highest derivative is positive. Yeah. Again, there's generalization of positive. Yeah. So if you think Routh-Hurwitz criteria, also it's nice. Yeah, because the coefficient on the highest power should be positive. Right. So that's already something nice that's happening. Okay. But since we are in the world of Lyapunov and energy functions and so on and so forth, we are going to actually construct a storage function, right? For passivity, we need a storage function. Okay. What is the storage function? This guy. Yeah. And in the context of what Antonio talked about, this is the energy of the system. Okay. Why? Because by introducing this element, okay, this element is somehow a spring element. I don't know if you understand this, see this or not. Yeah, this is like a spring. Yeah. So this is sort of a spring energy. Yeah. And spring energy is what? It's like half kx squared, right? This is spring energy type of a term. And what is the spring energy? It's potential energy, always potential energy. Spring energy is seen as potential energy. So we sort of created a fake spring. Where is this spring connected? Yeah, it is very interesting. This spring is sort of, if you have this initial state, I am just going to draw this kind of a revolute joints only to make my life easy, and say this is the final state. Yeah, this is set point, right? And so what am I trying to do? I want to go from this angle to this angle, right? And this angle, say I measure from horizontal. So I want to go from this angle to, well, actually maybe better to measure it from this guy. Suppose I measure from this guy. No, I should measure from horizontal. That was easier. I apologize. Because this is also measured from horizontal. I am measuring all angles from the horizontal. Okay. So this angle I want to go to, I draw a parallel here. So I want this to go to this guy. Yeah. Makes sense? Yeah. I am just trying to go to fine, that's okay. Yeah. So I want to change these angles in this way. The first angle goes here, second angle goes here. Alright. Now what is this spring? This spring is an artificial spring that is pulling me. There is one spring between these and one spring this way. You can think of it as two torsional springs, fake torsional springs or pseudo torsional springs. which are making me move from here to here and here to here. Yeah, it's so this is a very standard thing in robotics. Just like you think you give waypoints to quadrotors and then the quadrotor moves from one waypoint to the other. Then when you design a control, in reality, not in reality, but in pseudo terms or in energy terms, what you are actually doing is you are creating a spring with center at the waypoint. And then the control is sort of pulling it towards that waypoint. You can just think of it in your mind. In your head, if you think like it, it makes so much more sense that all I'm doing is giving it there's a spring connected to my waypoint and then to my quadrotor body, and it's just pulling it. So it will get to that point. Or you can think of it a damped spring, so obviously it stays there. Yeah, you pull it, then the next waypoint pulls it, and then the next waypoint pulls it. Okay, so this is exactly like that. I'm creating an artificial spring. Yeah, and that is the spring energy. This term is just the spring energy, it is a potential energy. Okay, and this term is obviously the kinetic energy, right? Anything with the velocities is the kinetic energy. So I constructed a potential. So in terms of what Antonio was saying, the storage function is also actually an energy function. Yeah, just that I've created some fake pseudo energies. Yeah, which should not be so worrisome for you, because that's how we design Lyapunov functions. Yeah, we are creating some pseudo energies anyway. That's the whole idea. Yeah, so great. Once I have this constructed, I'm just going to take the derivative because I want to claim that v dot is less than or equal to some u transpose y and so on and so forth. So basically the same deal as energy gained is less than or equal to u transpose y. Okay, great. So what is the derivative? E dot m e double dot, that's the first term. Yeah, because the half goes away because it's quadratic. Similarly, I get E transpose Kp E dot, the second term. But I have an additional term, yeah, which you should not forget. As you can see, I also had forgotten it. Very easy to forget. So I wrote it later on. Yeah, m is time varying, right? M has variables in it. It's not constant. Yeah, if it's constant, great for you. But usually, never will it be constant for any robot. Yeah, just think about it. This arm is moving in a fixed frame, okay, but the second arm is moving in the frame of the first arm. Okay, so it will never be a fixed M matrix. It will. So if you think of inertia now think inertia. If I want to write the inertia in a fixed frame, I mean you have to choose some frame to write the inertia. If I choose to write the inertia in this frame, then this is okay, will be fixed. Well, this will also not be fixed actually, because as this moves, there is a problem. But suppose I choose this frame to write my inertia, the rotating frame, but then this guy is still rotating with respect to that frame. Yeah? So if your object is moving in the frame, then the inertia is changing, right? Just like you think of this fan. Yeah, if it's on, yeah, right now I'll put a frame on that, the thing that is the beam that is with which it's hanging. Inertia is constant, right? Because the mass distribution is constant. Fan is not moving. I turn on the fan, it's not constant anymore, right? Because, no. Yeah, you seem confused. How? Really? Mass distribution remains the same even if the fan is rotating? Where is the mass on the fan? On the fins. Yeah, the center object, yes, it's a symmetric object. What you are thinking is symmetry. Correct. If it's a symmetric object, which is the center disk, sure, that inertia mass distribution doesn't change with rotation because all directions are the same, doesn't matter. But the fins, they have mass, right? And their location keeps changing with respect to the axis, and inertia is nothing but mass distribution. Your mass distribution is time varying. Okay, so if I write the inertia with respect to that fixed frame, my inertia is time varying or state varying. Yeah, it's not actually time varying, it's state varying. Just like that, you will have, for more often than not, you will have state varying inertias. Okay, very obvious. Yeah, but it will not depend on so that it will not depend on q dot, it will depend on only the q. Okay, the not the velocity states, it will depend on the position states only. Yeah, so there is also an m dot q, okay, which is the time derivative of m, by the way. Yeah, you can think of this as a little bit of abuse of notation. This m dot is actually dm by dt, the total derivative. So it's actually partial of m with respect to q times q dot. Okay, so remember that it's just, I have just written it like this. And now I am claiming this is less than equal to v transpose y. Okay, this is what you have to prove. You have to find the output. Notice I already used the new input. I am using the new input. I am not using the old input anymore. I am claiming that this is less than equal to v transpose y. What you have to do is you have to use this fact that m dot minus 2c is q symmetric, that is any quadratic form with m dot minus 2c is 0. You have to use this and you will get a very nice y. You will get a very nice y. If you remember, I don't know, it's like not in this example, but it was somewhere. Energy shaping, in this energy shaping, whatever, this example, this was interesting, this energy shaping stuff. He had passivity with respect to q dot. In this case, if you remember, he got passivity with respect to the q dot variable. Okay, so accordingly you have to, I don't know if you remember or not, but in this case the passivity was always with respect to the q dot variable. See if you, you had something like this. Okay, so anyway, so basically in this case also what I need you to do is complete the v dot expression and you should get something like a v transpose y for some y. Okay, you have to come back and tell me what is the y. Okay, and you have to of course construct a feedback. This is pretty easy. Once you have a y, your feedback is just v equal to minus phi y, such that y transpose phi y is positive definite. Pretty easy actually. I mean, if your if you get a y, the simplest feedback is minus ky itself, as you can imagine, right? We already did this in this example. Right. Because it's v transpose y, right? So if you know the y, then you construct y as minus ky, then v transpose y is minus k norm y squared, negative definite in y. Okay, so that's already done. You can of course construct, you see, these saturated controls also, like this minus k tan hyperbolic y. This just ensures that your control remains within some range. Okay, like a saturated control. Alright, but otherwise, once you identify a y, doing this is very easy. However, you have to also ensure that, or show in this case, that with this particular output y, you get zero state observability. This was a little bit more work. So basically, what is the zero state observability? It is that if the output you chose is 0, then the state also has to be 0. There is no other way about it. Or if you want to define it the way I defined it, the set of outputs the set containing output equal to 0 can contain nothing but the trivial solution, that is x equal to 0. Okay, so you have to also show zero state observability, because only with these two conditions does this control work. You need two conditions, not just passivity. You also need the zero state observability. Alright, okay.